Hello, I'm Richard Palethorpe. I'm a systems developer, and this is a video on the raw Fuse interface. So Fuse allows you to create file systems in user space, at least on Linux, maybe some other operating systems. And this video is about my exploration of the raw interface. So the raw interface is usually at dev/fuse. I previously did an article on libfuse and Zig, and there's what you can see in front of you now is my article on the raw interface. And in this video, I'll just talk a bit about that, and I'll show like my debugging and exploration setup. So this is like a very shallow. In terms of Fuse itself, this is quite a shallow introduction. One of the interesting things about the raw Fuse interface is there doesn't really seem to be like official documentation or a specification or anything like that. Most of the time you'd use it with libfuse, which removes a lot of the complication, or you'd use like one of the alternative implementations, like there's a Go library, there's a Rust library, so yeah. But yeah, I decided to take a look at the raw interface because just because it's interesting. And after I did the last article, I then found that there is a heap spray technique which takes advantage of Fuse, so that's useful for exploiting bugs, which is something I've been looking at recently, sort of how to do that. And I decided while I was looking at Fuse again, I'd try using the raw interface. And again, I'm using Zig just because I like Zig. Okay, so yeah, that's the article. Right, so my debug setup. I didn't look at libfuse much, except in one case where someone contacted me and said that they've seen some strange behavior in it. But yeah, I mostly just looked at the kernel itself, and I looked at what happens when I try to respond to messages from devfuse. So I have my Zig program. This is the finished article, so it's quite long now. But initially, I just opened devfuse and started trying to process messages, and that's where I begun. I also looked at the kernel code, which is defined in this directory fsfuse, and I looked at the dev.c, which appears to be like the main entry point for this, and I also looked at the header file. Where's that? Fuse H. This is the Linux header file that comes with the Linux kernel. And I automatically converted this into Zig using the Zig tool to do that. I covered that in the first video and article, I think, on libfuse. And I just copied bits of that into my final program. Yeah, you can see the automatically converted header just there. And I just copy bits of that into here. And you can see just from the C header, like the basic structure of the messages. The Fuse protocol is a message protocol with like a pretty simple message structure, and you can see all that just from looking at the header. Of course, you don't know what the messages really do, but you can guess, and you can just start reading in those messages. It's the kernel that sends requests to you. You're the one with the daemon, and you just respond to those requests. So first of all, it sends the init request, and that's where I begun. And yeah, the second half to this is, I mean, I guess you could just like completely guess what's going on and just try to implement stuff from the header, but it's probably a bit quicker and more direct if you have the kernel open and you have a debugger attached to the kernel. So I've not done a huge amount of work before with debuggers. In the process of trying to exploit a bug, I've started learning quite a lot more about GDB, and actually I use pwn-debug, which I discovered, which has a lot of nice extensions to GDB. So what I have is I have a VM which has I have like a custom VM setup which has a init written in Zig, and I have a BusyBox that I've dragged in there. So it's like a really lightweight VM, and that's it. It's booted. I start it with a script that runs it in QEMU, and it has the GDB stub running on this QEMU instance. So if I now go and start pwn-debug, which yeah, it's much nicer than raw GDB, and then I can connect. Let's get the connection command from my history, and right now we've connected to the VM, so I can't interact with that anymore. It's paused the VM, and you can see here that it's showing some context for where we've paused, which is in sort of like the idle code where the CPU puts the kernel to sleep, or the kernel puts the CPU to sleep, one of those. Okay, and at this point we can set some breakpoints. So we can set a breakpoint at actually, first of all, we need to load the fuse symbols. I have fuse compiled as a kernel module, and in pwn-debug I also have the kernel scripts loaded. The kernel comes with some Python scripts for GDB, which allow it to detect what kernel modules you have loaded, and you can run the lx symbols command and it'll load the symbols for those kernel modules. So just turn that off. Right. Okay, so we've loaded the modules for fuse. Now we should be able to find this breakpoint. Yeah, why not? Okay, we can see we've got lots of fuse symbols, and yes, first of all, we want to set 2 breakpoints, which I have discovered. One of them is fuse simple request. This function is used in most message handlers for fuse, at least most of the ones I've come across. However, it's not used in the init function. So if we go to dev, can't remember exactly where, fuse init, init in, init out, that's a struct. This is a function. That inits the module, so that's not correct. Use dev init. Not sure that one is the correct one either. Maybe if we look for the structure, fuse init, there should be a structure. Yeah, init in. I think init in is the one that it sends to us. Yes, and we can search for references to that. We have one in inode. Fuse init. Let's see where this occurs. This one occurs here. Process init reply. That sounds like a good function. Use send init. Okay, let's put a breakpoint at fuse send init as well. You can probably tell that I've forgotten exactly which function that I was supposed to set a breakpoint at to get init. Okay, and then if we continue, then let's run our test. You know, this I've actually, of course, I've like fully written the test now. So, okay, here we go. We've hit that breakpoint, so I managed to get the right function which calls init. Actually, let's switch. I've got my face in the way of pen debug's output, so let's switch that. In fact, let's make that full screen so that we can get all of this. Okay, so got a whole bunch of information here. I think I probably pay attention to about 10% of it. At the top here, we've got some information about the CPU registers. I'm not entirely sure what this all means. I've still got some learning to do on the pen debug's output, but useful information does appear here. Because we're compiling with, I believe we're compiling with quite a high optimization level. So sort of the high level code that we have here often doesn't doesn't translate directly into the disassembly, which we can see here. These are the instructions. So sometimes it can be really useful if you want to know what a variable is actually set to. It can be useful to look at the registers and the disassembly to try and figure out where the real value is for that variable, because quite often you'll try looking up a variable. Let's try it with flags. Okay, that one's there. It's about FM. That's also there. Quite often you'll find that a variable is optimized out. So yeah, it can be useful to try and look at the disassembly and the register values to try and figure out what that variable's value would be. Okay, I'm not sure. Yeah, right. So where were we? We're in the init function. We can see the backtrace here, and it gets called as a result of mount. So I call mount to mount the file system that we create. A bit of an interesting backstory to how we call mount, which is in the article. And yeah, basically we open dev-fuse and then we call mount, and apparently, as we can see here, calling mount triggers the init message. At least that's how I interpret this. So the first time that something tries to mount the file system, we'll get this init message. It does some interesting stuff here, like it calls VFS get tree. VFS is the virtual file system layer. So this is like something that gets called for all file systems and does something quite important. Okay, so let's continue now. So I thought once we'd handled the init message, all right, we seem to have hit init again. That's interesting. And then inspected as well. Okay, how have we managed to hit that twice? I don't know. Okay, there's always some mysteries left. Let's continue again. What's actually happening? Okay, it says it's handled that message. We've hit the breakpoint again. Okay, I mean, sometimes it happens. I guess this could be a result of the compiler reordering stuff. You often find that when you're debugging again, because the optimization level is quite high with the kernel, you find that the debugger jumps around and unexpected things happen. I don't know if that's what's just happened here, but I guess it could be. I don't know. Okay, so now we've hit the fuse simple request breakpoint. I thought initially, looking at, I keep going to the wrong place. I thought initially that we'd get the lookup opcode, because I thought, the first thing we try to do is set an extended attribute on a file, and the first thing we need to do is look up the path to that file to get the inode for that file. I explained in the article what I'm trying to do with set extended attributes, so I won't go into that. But yeah, I thought first we'd get lookup, but what I discovered when actually doing the debugging, and also what the debug output of the program would actually be as well, I discovered that we actually hit another message. We can see in the backtrace, it's pretty clear what that message is. We start walking the path to find the inode, and then we have a permission check on the inode, and then this calls fuse permission, and then this triggers get attribute. Now, we look at args that is passed to fuse simple request. We can see that it's got an opcode number of 3. If we go and check this opcode number, I really wish I'd stop doing that. Go and check this opcode number. Yeah, get attribute number 3. So the first message we actually get is get attribute. Okay, and we can inspect. Look into this further in the debugger. It's not really necessary, but you can see what it's sending us here. It's actually, this pointer contains the real function arguments. Because it's void, you have to cast it to the real thing. But we can inspect this from the debugger side. We can also look at the Zig output. We go and go down here. When I receive a message I don't recognize, somewhere down here, where are we? Okay, this is where we handle the messages. Yeah, see, we switch an opcode, and to begin with, before I had any handlers, I just print the opcode here. Also at the beginning of this function, I print the message header and stuff like that. If we look at the Zig output, you can see that when we receive an opcode, we just print this out in Zig. So kind of an alternative to looking at it in the debugger. We can look at it either way. Okay, so the first thing we actually get is attribute, and we go and look at what I actually return for that. Yeah, I basically just guessed a bunch of values or deduced them from the kernel code. So this particular field in our response valid, I looked at the kernel code and what it does with valid, and I guess that it's the time when this attribute entry stops being valid. And so I take the current time and just add 300 seconds to it, or 5 minutes, and hopefully we'll never get another get attribute for this particular inode. The actual inode that we received this message for appears to be like the root inode of the file system, or whatever that is. And I just like set some of the silly values, like the number of blocks to 1, size of 42. I guess the kernel would accept anything for these things. Userland tools may actually struggle if you start putting in really silly values, but frankly nothing's actually going to use our file system where that matters. I guess that like the mode should be set to a directory, so I'm just guessing that this is like the root directory of our file system, or the mount point, or superblock, or something that I'm supposed to know the name of, and then set the permissions so anyone can read or write to it, whatever. Again, the kernel seems happy with these permissions. Set the number of links to 1. I guess it'd be happy with any number of links except 0. If you set it to 0, that might cause some weird behavior. I don't know. And set the user and group to, whatever our current user and group are. So we plan to run everything inside the same executable with the same user and group, so that should be fine. We could also just set it to the user and group that the request header has. So, whatever user makes a request, it'll always be the user which that file belongs to. Whatever, dev probably should be 0 or nothing, or whatever, it doesn't matter, and flags whatever. So the kernel seems happy with these values and allows us to advance to the next stage. So the next stage was what I expected. Let's continue. And we've got another request, and let's look in the Zig output. Zig is a nice feature where it just prints out a structure using reflections. That's what you can see in this kind of messy output. It's not the prettiest outputs, but it's like really easy to start getting some debug output. Okay, so we can see that we handled get attribute. Those are the inputs for that. And we've now stopped on another one, and this time we can see that it's fuse lookup, which is what I was expecting. And look at args. We now have an opcode of 1, which is the correct opcode for lookup. So now we're on to what we expected. And if we go and look at the handler for lookup, is this working? Okay. Apparently that doesn't work as I expected. I was just trying to find the location where that's used. Okay, so if we look at the handler for lookup, turns out that the lookup message is actually sort of like a superset of get attribute. The main difference is that we now have an opportunity to set the inode number, which I've cleverly set the inode number to the similar looking value in hex as the actual name of the file, which is both foo. And yeah, mostly the same stuff as get attribute, but we also set the entry valid time, which I guess is the time which the mapping from file path to inode number is valid as well, which I just set same to the attributes time. So it's just like a superset of get attribute and lookup. And that's that. Then we handle that. That was fairly straightforward. And then next, what do we have? Okay, we hit simple request again. We can see that we've handled lookup. This time we have opcode 21. We can also see that node ID is 3840, which in hex is oxfoo. So we can see we've been successful in setting our inode. And this opcode 21, that is the opcode of set extended attribute. So we're now handling set extended attribute, which is the one we are really interested in, or one of the ones we're really interested in. So in the debugger, we can actually, without waiting to without having to write the zig code to parse the set extended attribute arguments, where are they? So set extended attribute in. So without actually writing the zig code to actually inspect what arguments we're going to receive and pass them and display them, we can look at this just in the debugger. Which sometimes is an advantage to this if you're really not too interested in actually writing the parsing code. However, there is one slight complication. Because this is a generic structure that we have here, the inargs are, yeah, let's have a look. Inargs is an array. It's an array, and we have like 3 objects in there, and the values of these objects are void. However, we know that because this is set extended attribute, these values should be something like struct and then fuse, fuse, let's try this. Oh, okay, fuse in. Arguments that are sent to us always seem to have in at the end. So okay, we want to dereference this pointer. Okay. So yeah. So that seems to have parsed that correctly. There's a size of 3 and not much other information there. I've not got any flags set on the extended attributes, which is good because I didn't set any flags when I was making the call. Yes, we can just we go and check my actual test code. You can see like I make a really basic call to set extended attribute. Just have the attribute name, the value, which is Baz, and I think that's just the size of the value. So this matches up with what we have here. The size is 3, which is the size of the value I set. But possibly there's an easy way to decode this information, because we look at the call trace. We previously were in a function called fuse set extended attribute, and we can go up into that function. You can see now we're in this function, and we can see here that the inargs was set in this function, and maybe in this function we have some variables we can look at. So I really wish to stop looking at the web page. Yeah, so there's possibly some variables we can look at. We can look up this function in the code. What's it called? Fuse set extended attribute. Okay, this is the function, and there's some stuff in here that maybe we can look up. Yeah, we have actually the arguments to the function contain name and value. We can see where these are put in down here. We can check these in the debugger. So we see if we can print this. Okay. Okay, yeah. So that prints it. The name is user.bar. We have to put user dot in front of it. That's the namespace for the extended attribute, and bar is the actual name. And then if we try printing the value, okay, it's void, but I guess we can cast it to try casting it like that. Okay, and we print a load of nonsense, but at the start there you can see that like baz. So yeah, it's not a null terminated string. It's actually just binary data. I can't remember the exact commands in GDB to print three letters of an array, so I won't bother trying. So there we go. We can get all that information pretty easily. Let's continue. We've hit another breakpoint, and this was unexpected by me. I was expecting at this point for my test to be over. So, right. Yeah, at this point we've handled all of the stuff I was expecting, plus get attribute. We've handled set extended attribute, and I was expecting at this point for this system call to return and us to be finished. However, we've been sent another message, and originally I didn't have this function down here. What this function does is it checks that there's no more messages. So I developed most of this code without having this function here, which is really useful because yeah, it checks that we haven't got more stuff waiting in the pipeline. So what happens is if you don't handle a message, then you just hang inside this system call, and this system call, as far as I can tell, like it will just hang forever. This is like a kind of a problem with Fuse actually. For example, if you're using the SSH Fuse file system, which I use a lot now, it's really useful. If you get disconnected from the host and you have some program running that makes a system call that interacts with the mount, and there's no timeout on that system call, then it can hang for a long time. I think eventually it will, depending on your SSH settings or whatever, like it will eventually cancel all of those calls, but like you can end up with like frozen applications because they're just waiting in a system call that is actually waiting for a remote file system. And you know, a lot of system calls, they never were intended to be used with like a remote file system. It's like something that wasn't designed into Unix or, you know, whatever Linux inherited from the past. So yeah, you can easily get stuck, and I was just getting stuck here. The next mistake I made was that I'd set various breakpoints to various functions that were specific to, say, set extended attribute. I think I'd actually set a breakpoint go back and maybe like set a breakpoint to fuse set extended attribute. And I was returning from the debugger just here, and I was looking at error no, and I was thinking, okay, error no is 0, so now we should just, you know, basically return, okay, there's a function here, but it, you know, like nothing, whatever this function does, it's just called for its side effects, so it probably doesn't do anything interesting, and when we return error, and like we should be all finished, but that's not the case. Yeah, what actually happens is that if you look at the stack trace here, or maybe if I try printing the full backtrace, yeah, you can see we go through set extended attribute, and then we call fuse update ctime, and then we go into like some stuff that I've not seen before, fuse flush time update. I mean, basically what this is doing is just updating the timestamps for this inode. And as part of this, we end up going into fs write back, and we go through quite a complicated call chain. I mean, it looks actually fairly simple when you look at it here, but if you're sort of going through, I mean, what I did, and this didn't work very well, is I just started like looking in here, like, okay, what functions does this function call? And like you start going into fuse get inode, and then it's quite a shallow call chain, but yeah, basically you start going into this, and then you start seeing branches, and basically there's quite a lot of stuff to sort of read through here and see, you know, whether this function does anything. Okay, we've sort of started going into a loop there because clang d doesn't actually get where those things are defined. Yeah, basically start going into this call chain, and you start getting into sync inode metadata, write back single node. We're into all this stuff here, and it's not instantly clear like whether this function calls anything that could be causing us issue. If I'd had a breakpoint set at fuse simple request, I'd have quickly seen that, yeah, basically we have another message that's sent to us. And yeah, even from this callback, it's not really clear what that message is. Fuse flush times, whatever. It turns out that it's this opcode here is number 4, which opcode number 4, set attribute. Okay, so yeah, basically, and this is like in retrospect really obvious, when we have to update the time to an inode because we did something to it, we set an extended attribute on it, so we need to set the updated time on it. We need to set the attributes on that. So in the end, there we go, that's better. In the end, we set the attribute again. So yeah, I guess the lesson here is to make sure that, or try to make sure that when you're doing something like this, you have a number of fail safes that like if like some extra action is required on your behalf, you'll know about it. Because what was happening to me was the debugger was just like I was clicking continue, and the kernel was going to sleep, and the debugger, the kernel was going to sleep waiting for us to respond to get attribute, and the debugger was just going into just doing something like this basically. It's just going continuing. And this was just, this user space program was just hanging. So yeah, hopefully I'll remember that lesson. And that's it. So we handle that. Yeah, the details are covered in the article, as well as details about SIG and whatever. Okay, so my head's gone blank. I guess that's it. Really nice tool, Pen Debug. Again, not really used it much. It's kind of new to me. In the past, I've used all kinds of tracing tools. Linux has so many ways of tracing something. I mean, starting with kprintf, but of course you have to recompile the whole kernel or whatever. And then it has ftrace, which, you know, you don't need to write any code to use that. You don't need any tools installed in a VM to use that as well. Yes, where is it? Have I got it mounted? Yeah, whatever. Yeah, there's ftrace, which you can just set trace points by entering details into a file. Ah, that's it. Debug. Yeah, I mean, all you need to do is just set up events by echoing text into sys files. Not user-friendly or discoverable in any way, but you don't really need many tools inside your VM or your system. You just need to have this this debug and tracing file system mounted. It's not always mounted on all file systems, so you just have to make sure that's mounted, and then you can start using that, and you can do really advanced stuff just, you know, by echoing and whatever into those sys files. And then there's perf, which uses this interface but provides a much nicer way of doing things. It can access kernel debug data and whatever. I don't know if I have perf installed. No. And then there's bpf trace, which again, like, is even nicer. Can do really advanced stuff with that, and the whole, like, loads of other tools which can trace the Linux kernel. And then you have GDB, which GDB seems to be really popular with security researchers and Pwn Debug, and then, like, these other tracing tools seem to be more popular with performance people, but they're both really useful. There's kprobes as well, I suppose, where you can actually write some C code and insert that into the kernel. That's really popular with, at least with SUSE kernel developers. So yeah, I think that's it. Otherwise, I'll just ramble on a bit more. Again, yeah, this is kind of just an accompaniment to the article, so please go and check that out. And also, if you have any questions or whatever, come and talk to me. I'm happy to speak to people. And that's it. Thank you for watching all of this video. Stop recording.